Okay, so welcome to section 9.5, which is matrices. Okay, so definition. What is a matrix? Well, a matrix, that's what we're defining, is a rectangular array of entries how do I want to say this? Entered in M rows and N columns. Columns. The entry in row I and column J is denoted by A sub ij, and the matrix is given by either 1, a capital letter, A, B, etc., or 2, a bracketed A sub ij. A sub ij would be how we would annotate the matrix. Okay, so for example, or actually let's note first the dimensions of a matrix A with M rows and N columns is given by M cross N rows, that is, i.e., that is rows by columns. Rows by columns, always rows first, always rows first. Rows by columns. So for example, so find the dimensions of the following matrices. Find the dimensions of the following matrices. As well as the indicated entries. Okay, so number 1, let's say we have matrix A is given by, so it's a matrix, it's always going to have this square bracket. So let's say first column is 1, 2, second column is 3, negative 9, then 4, 0, and then maybe 7, 5. End bracket. Okay, so I'm going to rewrite A neatly. So I have 1, 2, 3, -9, 4, 0, 7, and 5. So I want to know the dimensions. So the dimensions are rows, by columns. So that's going to be 2 rows by 4 columns. So this is the dimension. Actually, let me write that above as well. So the dimension of matrix A, so let me be even more thorough. Dimension of matrix A is 2 by 4. Okay, but now let's say what is A sub 1, 3 and A sub 2, 1 equals question mark. Okay, so A sub 1, 3, always rows before columns, is going to be the entry that's in the first row and the third column. So the entry that's in the first row and third column is 4. Now if we have, let's do A sub 2, 1. So 2, 1 is the entry that's in the second row and first column. So that's 2. Okay, so that's how we indicate the entry is row column in the subscript. Row first, column second. So number 2. Let's say we have matrix B is given as first column. Let's do, 1, 2, 3, then 4, 5, 6, then 7, 8, 9. Okay, so rewriting matrix B. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So what is the dimension? We know that the dimension of matrix B is going to be rows by columns. Okay, so how many rows do we have? 1, 2, 3, so that's 3 by, how many columns? 1, 2, 3. So 3 by 3. So dimension of matrix B is a 3 by 3. Okay, now let's find some entries. Let's do B sub 2, 3 and B sub 3, 1 equals question mark. Okay, so B sub 2, 3 means the entry that's in the second row and the third column. So I claim that that's 8. And B sub 3, 1 is going to be the entry that's in the third row and the first column. So I claim that that is 3. Okay, let's do another one. Subscript number 3. So let's say I have matrix capital C is given by, let's do 1, 0, 4, 2, 9, 5. Okay. And before I go on, let's say we want to find entries C12 and C21 equals question mark. Okay, so first let's rewrite C. We have 1, 0, 4. Then we have 2, 9, 5. Okay. Okay, so I know that the dimension of matrix C is going to be rows by columns. Rows by columns. Okay. So the dimension of matrix C is going to be how many rows? 1, 2, 3. By how many columns? 1, 2. So it's a 3 by 2. And the entry C sub 1, 2 is the entry that's in row 1 and column 2. So I claim that that is 2. Whereas C sub 2, 1 is the entry that's in row 2 and column 1. So I claim that that's 0. Okay, so hopefully this makes sense so far. Okay, so now let's do matrix addition and scalar multiplication. So matrix addition, and by addition I include in that subtraction slash scalar multiplication. Oh, actually let me write and scalar multiplication. Multiplication. So scalar means by a constant, not by another matrix. So let's let capital A and capital B be M by N matrices, meaning they both have the same dimensions. It's required here. And let's have K be a real number. Then, number 1, A plus B will be the matrix that is A sub ij plus B sub ij in each entry. And we will go over what that means in a moment. Number 2, A minus B will be the matrix where each entry is A sub ij minus B sub ij. That is, we subtract corresponding entries. And finally, number 3, if I have K times matrix A, I take each entry in the matrix and multiply it by K. Okay. So let's do an example. Okay, so let's let matrix A be equal to square brackets always. Let's do 1, 2, 3, 4, 5, 0. Square brackets. Okay, and let's have matrix B be equal to, has to be the same dimensions in order to add and subtract. So let's do 0, 1, 4 and 9, 2, 3. Okay, so evaluate the following. Number 1, let's do A plus B. So A plus B is going to be, so matrix A is 1, 2, 3, 4, 5, 0, which I'm going to add to matrix B, which is 0, 1, 4, 9, 2, 3, okay, so what we get then, the resultant matrix is going to add term by term. So the first entry will be 1 plus 0. The second entry will be 2 plus 1. The third entry will be 3 plus 4. That's the first column. Now let's go to the second column. It'll be 4 plus 9. Then it'll be 5 plus 2. Then it'll be 0 plus 3. Okay, so 1 plus 0 is 1, 2 plus 1 is 3, 3 plus 4 is 7, 4 plus 9 is 13, 5 plus 2 is 7, and 0 plus 3 is 3. So that's the sum of A and B, matrix A and B. Notice why they have to have the same dimension is so that we can add. Okay, so now number 2. Let's do A minus B, shall we? So it'll be the same setup, A minus B. So that's going to be, let me just copy and paste these guys. In fact, I could copy and paste most of this, save you some time. And all I'm going to do is change everything that was orange to pink and everything that was plus to minus. Okay, so it's A minus B, which is going to be the matrix that takes the first entry minus the second. A's entries minus B's entries in each position. Okay, so what does that give us? What is the difference now? A minus B. 1 minus 0 is 1. 2 minus 1 is 1. 3 minus 4 is negative 1. 4 minus 9 is negative 5. 5 minus 2 is 3. And 0 minus 3 is negative 3. Okay, there we are. So far, so good. Okay, so number 3. What's a good number? Number 3. Let's do 5 times matrix A. So 5 times matrix A means that for each entry in matrix A, well, this will be 5 times the matrix. I don't know if I want that to touch the bottom. It'll do weird things. So 5 times the matrix. One, 2, 3, 4, 5, 0. So what I'm going to do is I'm going to push the 5 inside the matrix. So this will be 5 times 1, 5 times 2, 5 times 3, 5 times 4. Each entry gets multiplied by 5. 5 times 5. And 5 times 0. So when you multiply a matrix by a constant, you just go ahead and multiply each entry in the matrix by that constant. So what we get then is going to be 5, 10. Actually, let me do it in green, because that's what the color I chose for this. 5, 10, 15, 20, 25, and 0. So there we are. Hopefully that is making sense. Okay, now comes the hard part, and it's matrix multiplication. So you'll have to bear with me. It does take a while to get used to. So matrix multiplication. Okay, so let's let A be an M by N matrix, and B be an N by P matrix. Then the matrix product AB results in an M by P matrix whose entries C sub I j are found by, how do I want to say this, taking the sum of the products of each of number 1, matrix A's row I with number 2, matrix B's column J. Okay, so that is, i.e. it est, i.e. C sub I j is going to be A sub I 1, B sub 1 j, plus A sub I 2, B sub 2 j, plus dot dot dot, plus A sub I n, B sub n j. Okay, so notice that it goes to the n columns for A and the n rows for B. Okay, so let's note. How does this look visually? So note. Visually, the product is as follows. So let's say we have matrix A times matrix B. And that's going to be some matrix we have here. And this will be A sub, actually, maybe I'll do it like here. So A sub I1. Yeah, I should have given myself more room. A row I column 2, row I column N. And all the rest will just be dots, placeholders. Okay, so we've got a whole bunch of entries in a rectangular array. And then B is another matrix. But this time we're going to go to B sub 1J, B sub 2J, B sub NJ. So it's always column J, but the rows count 1 through N. And we'll have a whole bunch of other entries. So if I take how do I want to do this? Let's do the pink. That's not light enough. Let's do a lighter pink. And a thicker pen. So if I take this row here, I don't know if I like that. I think I want a lighter color. Okay, that's good. Okay, and a thicker pen. So I'm taking row I and column J. And when I do that, what I get, when I do this multiplication, the entry for the product C sub ij is going to be the sum of the product of all of those guys. So C sub ij, of course, will be is going to be A I1 multiplied by B1J, to which we're adding A I2 and multiplying that by B2J, plus dot dot dot, plus finally A I-N times B-N-J. So notice I use the rows for A and the columns for B to find the entry. Okay, so I call this the finger trick. I always like to use my index finger on my left hand to do the rows of A, and my index finger on my right hand to do the columns of B simultaneously, so that I can see where I am. So for example, let's try and do this. So find or evaluate, I have ants on me again. So find the following matrix products. Matrix products. Okay, so number 1, let's say we have A is equal to, let's do 2, 4, 1, 7, 3, 5. And let's have B is equal to let's do 1, 0, 0, 1, and 2, 3. So AB is what we're looking for. Okay, so notice that A is, what are the dimensions here? So how many rows does A have? It has 3. How many rows does B have? It has 2. How many columns does A have? It has 2. And how many columns does B have? It has 3. So I claim that B is going to be a 3 by 3. And let's see, because the two inner dimensions match, they have to match. Check mark, they match. So we can evaluate the product. But the inner dimensions have to match. Okay, so let's have A times B, which is going to be matrix A is 2, 4, 1, 2, 4, 1, 7, 3, 5. Matrix B is 1, 0, 0, 1, and then 2, 3. Okay, so I claim I'll get a 3 by 3. So I'll get ready for this. But what is the entry that is in the, how do I want to do this? First row and the first column. Well, I claim that'll be 2 times 1 plus 7 times 0. So notice I've taken each entry in the row of A with the column of B. So actually let me move this down so I can do this more explicitly. Okay, so what is the entry in the second row? So I claim that that'll be 4 times 1, because I'm still in the first column, plus 3 times 0, because I'm still in the first column. However, I'm in the second row. So the rows are from A, the columns are from B. Then if I go to the third row and first column, it'll be 1 times 1 plus 5 times 0. So those are the entries in the first column. Notice that these entries here are the whole matrix A, right? Whereas these entries are the first column of first entry in the first column of B, and then the second entry. So given that, I claim that if I were to do the second column, I would still have my 2, 4, 1, and my 7, 3, 5, which I would then multiply by 0, 0, 0, and 1, 1, 1, because that's the second column of B. So notice I've taken the whole matrix A and I've multiplied by the first entry in the second column and then the second entry in the second column. Okay, so now let's do matrix A again, which is 2, 4, 1, 7, 3, 5. And let's go on to the third column. So I claim it's 2, 2, 2, and then 3, 3, 3. And we are adding these. Well, if I could only do this a bit neater, maybe like so. Okay. Okay, so what do we get when all is said and done? We get 2 plus 0 is 2. 4 plus 0 is 4. 1 plus 0 is 1. 0 plus 7 is 7. 0 plus 3 is 3. And 0 plus 5 is 5. 2 times 2 is 4. Plus 21 is 25. 8 plus 9 is going to be 17. 2 plus 15 is also 17. So there we go for that one. Why is it not autocorrecting? Okay, so that is A times B. Notice it's a 3 by 3. So we have the 3 from matrix A and the 3. Those are the outer dimensions of A and B. Okay, so hopefully that makes sense. Let's see. Where am I? Okay, let's do number 2. Let's say we have A is 2, 4, 6, and 1, 0, 1. And let's have that B is equal to, let's do 2, 4, 6, 8, 9, 10, and let's kick it up a notch, 11, 0. So find A, B. Okay, so notice the dimensions. Let's see if the dimensions work for us to get. This is a 3 by 2 columns, and this is a 2 rows by 4 columns. So yes, the inner dimensions are the same. They match. So we can do the product. And my product will be a 3 by 4. So let's do this, and A times B is going to be matrix A. I'm going to do something, see if I can do this. Copy, paste, but I'm going to change the style to blue. Yeah, that works. Okay, and then matrix B, let's copy and paste. And I'm going to make this purple. Okay, so what do I get? So I claim it'll be a 3 by 4. Okay, so first I claim that this is 2, 4, 6, 1, 0, 1. And I'm going to multiply that by 2, 2, 2, and 4, 4, 4, and then add these guys together. And is that my row column? Move this a bit. Oops, no, let me not move that. The natives are restless. I'm hearing the ghosts in my room. It's far too late. It's nearly the witching hour. Okay. So, let's see. Row 2 times 2 plus 1 times 4. Yep, that works. Okay, so now let's do the next one, which will be 2, 4, 6, and 6, 6, 6, plus 1, 0, 1, and 8, 8, 8. Then once again, 2, 4, 6, and 9, 9, 9. Plus 1, 0, 1, and 10, 10, 10. And you should see that that's row, column, row, column. Finally, we have 2, 4, 6, 11, 11, 11, plus 1, 0, 1, and 0, 0, 0. Okay, so what do we have when all is said and done? So the entry in the first row and first column is 4 plus 4 is 8. 8 plus 0 is 8. 12 plus 4 is 16. So the next column we have 8 plus 12 is 20. 6 times 4 is 24. 36 and 8 is 44. 2 times 9 is 18, so that's 28 plus 10. So 4 times 9 is 36. 6 times 9 is 54, plus 10 is 64. 2 times 11 is 22. 4 times 11 is 44, and 6 times 11 is 66. So that is the product, A times B. And notice, actually maybe I should copy and paste this. What are the dimensions? And make sure I do that up here too. A times B, A times B. So the dimensions for this, we have 3 rows and 4 columns. And is that the externals? Yeah, those are the external dimensions. Okay, let's do another one. So number 3, is this number 3? Yeah, it's number 3. Okay, let's say we have that A is the matrix. Oops. One, two, ow, shoot, ouch, my goodness, something's going on. And let's have B be the matrix. 3, 4, 5. Okay, so what are the dimensions on A? Looks like 2 rows by 1 column. And the dimensions on B look like 1 row by 3 columns. So because the inner dimensions match, we can find the product, A times B. They have to match. Okay, so A times B for us is going to be matrix A. So I claim we're going to get a 2 by 3 matrix out of this small little thing here. So matrix A times matrix B is going to be, I claim it's going to be a 2 rows by 3 columns. So I claim that it's going to be 1, 2 times 3 times 3. Then it's going to be 1, 2 times 4 times 4. Then it's going to be 1, 2 times 5 times 5. And is that true? If I take the first row with the first column, it's 1 times 3. Yep, looks like it works. Okay, so I claim that AB is going to be equal to 3 and 6 in the first, then 4 and 8 in the second column, 5 and 10 in the third column. Okay, so there we are for that one. Okay, so let's note something about matrix multiplication. So note, matrix multiplication is not commutative. So matrix multiplication is what we call non commutative. Okay, so that is, i.e., it est matrix AB is not equals to BA. It's certainly the case that BA might not even exist, let alone be the same. So for example, so let's let A be the matrix, let's do 2, 4, 1, 3. And let's let B be the matrix 0, -1, 3, 2. Okay, so find AB and BA. Okay, so AB is going to be matrix A in blue times matrix B in purple. Note that the dimensions work out because they're both 2 by 2s. This is a 2 by 2. This is a 2 by 2. So the inner dimensions are fine. Okay, so what do we get? We get, well, I just take 2 and 4, multiply them by 0, 0, and add those two, 1 and 3, multiply that by -1, -1. Then I take 2 and 4 and multiply that by 3 and 3. Then I take 1 and 3, multiply that by 2 and 2. Okay, so I claim that matrix AB is going to be the 2 by 2 matrix uh, 0 minus 1 is -1, 0 minus 3 is -3, 6 plus 2 is 8, and 12 plus 6 is 18. So So that's AB. And now let's figure out matrix B times A, which is going to be matrix B is here, copy, paste, times matrix A is here, copy, paste. Okay, so now what we're going to get is 0, -1 times 2 times 2 plus 3, 2 times 4 times 4. Then again, we'll have 0, -1 times 1 times 1 plus 3, 2 times 3 times 3. Oh, and those should not have been pink. Should have been orange for this one, sorry. Okay. Okay, so what do we get then? We get that matrix BA is going to be the 2 by 2 matrix. A 0 plus 12 is 12. -2 plus 8 is 6. 0 plus 9 is 9. -1 plus 6 is 5. So notice that AB is not equal to BA. So BA is not the same as AB. Check mark. So it's not commutative, meaning it doesn't share the same properties as real numbers. Okay, so where was I? So properties. Let's do properties. Okay, I guess that's a good number. Good color. So properties. Of matrix multiplication. Okay, so there's the associative property. Associative. Which states that if I have A times B and then times C, it's the same that if I did A times the product BC. Doesn't matter. Notice, however, the order ABC is always the same from left to right. Okay, what about the left distributive property? Distributive property. Meaning that C times A plus B is C times A plus C times B. It's on the left. So let me underline that. It's on the left, left, left. Okay, so the next is going to be the right distributive property. So right distributive property. So A plus B times C is going to be A times C plus B times C. Notice now it's on the right. It's on the right. Okay, it has to remain on the right because it's non-commutative. I can't swap the order. Okay, so hopefully that makes sense. So let's do some fun things with matrices. if I can stay awake for it. So, for example, let's let matrix A be equal to 1, 2, 0, 3. Oops. Come on. Let's find A cubed. Okay. So what is A cubed? Well, A cubed is really A times A times A. So let me emphasize. We're going to multiply all of these. So I'm going to take A, change it into blue, and I'm going to multiply that by itself twice over. But what I'm going to do is I'm first going to focus on these two. So I claim that this is going to be matrix A times the product of A with himself. Okay, so what is the product with A with himself? Well, it's going to be 1, 2 times 1 times 1 plus 0, 3 times 2 times 2. For the first column, then it's going to be 1, 2 times 0 times 0 plus 0, 3 times 3 times 3. Okay, so what do I get? So we get 1, 2, 0, 3. Times the result of the product of A with himself, which is going to be 1 plus 0 is 1. 2 plus 6 is 8. 0 plus 0 is 0. And 0 plus 9 is 9. Nope, not going to autocorrect. Okay, fine. Okay, so now we're going to do the last product between these two guys, which is A and A squared. So it's going to be 1, 2 times 1 times 1 plus 0, 3 times 8 times 8. Then it's going to be 1, 2 times 0 times 0. Then I'm going to add to that 0, 3 times 9 times 9. Yep. Are there ants on me? Stupid ants. Times 9 times 9. Okay. Oops, wrong color. That's supposed to be pink. Okay, it's supposed to be pink. Okay, so what do we get when all is done? 1 plus 0 is 1. 2 plus 24 is what? 26. 0 plus 0 is 0. And 0 plus 27 is 27. Notice something interesting about the corners. 3, 9, 27. That's interesting. Okay, so there is a result for A cubed. Okay, let's do another fun one. So, for example, so consider let's do a matrix of the form A is equal to, let's do A, 0, 0, and then 0, and then B. Okay, so let's find A to the nth power for all positive integers n. Okay. Well, we have to do this. Let's do a couple. So A squared is going to be A times A, which is going to be, let's copy and paste, A times A. So that's going to be, okay, let's see if we can forego doing the intermediate steps now. Oh, maybe not. Let me, let me go ahead and show them once again, just because I just want to make sure we get this. Okay, so it's going to be A0 times A times A plus 0B times 0 times 0. Then it's going to be A0 times 0 times 0. Then we're going to add to that 0B times B times B. Okay, so what do we get? We get that A squared is equal to A squared, then 0, then 0, then B squared. Okay, so that's what we get for A squared. So let me write squared. Okay, now let's do A cubed. Well, I claim that that's just going to be A times A squared. So I claim that that's just going to be A, which we have here, and A squared we just found. Okay, so that's going to be A0 times A squared times A squared plus 0B times 0 times 0. And we have A0 times 0 times 0 plus B, sorry, what am I doing? 0B times, what do we have now? B squared, so B squared, B squared. Okay, so I claim that A cubed is going to be A cubed 0, 0, B cubed. Okay, so it looks as though there's a pattern here, right? So what would A to the n power be for any n? I claim that A, so therefore, because this pattern is just going to keep on repeating, A to the n is going to be equal to little a to the n, 0, 0, little b to the n, for all positive integers n. Okay, let's do another one. Let's let A be the 2 by 2 matrix, 0, 1, 1, 0. Why does it always autocorrect so oddly? Okay, so let's find A to the 2n and A to the 2n plus 1 for all positive integers n. Okay, once again, let's do this the long way. So we know that A to the first power is just himself, so let me try and redraw this a bit nicer. 0, 1, 1, 0. Okay, so what would A squared be? Well, of course, that's just A times A. Actually, before I paste, let's do A times A. Which is going to be A times A. Don't forget to make these brackets. So this is going to be 0, 1. Actually, let me make this purple. Okay, 0, 1 times 0, 0 plus 1, 0 times 1 times 1. Okay, so 0, 1 times 1 times 1 plus, where am I? 1, 0 times 0 times 0. Okay, so I claim that this is 1, 0, 0, 1. Okay, so before we move on, actually, no, we don't know what that is yet, so I can't state that. Okay, so let's try A cubed. Well, that's just going to be A times a squared. So that's just going to be a here times a squared here. And that's going to be 0 times 1 times 1 plus 1 0 times 0 times 0. Then 0 1 times 0 times 0 plus 1 0 times 1 times 1. So that's going to be 0 1 1 0. Notice that that's just equal to a again. Right, that's what we began with. Okay, so now let's do a to the 4th power. Well, I claim that that's just a times a to the 3rd power. So that's just going to be a, and I know that a to the 3rd power is here. So that's just going to be 0 1 times 0 times 0 plus 1 0 times 1 times 1. And then 0 1 times 1 times 1 plus 1 0 times 0 times 0. So that's going to be 1 0 and then what is that? 0 1. Notice that's the same as a squared, right? A squared. Okay, so what's going on here? I have a feeling that all the evens are the same and all the odds are the same, but let's do one more. So a to the 5th. I claim that that's just a times a to the 4th, which is going to be a, which I didn't finish the bracket, a times a to the 4th Notice something. Actually, I'm going to make my life easier here. Do you agree that this is the same as a times a squared? A times a squared. And let me show you explicitly why. So let's just copy and paste all of this. Copy, paste. Why is this the case? Well, if I change this to pink, maybe it'll be more obvious. they're exactly the same matrix, green and pink. So, and this is just A times A squared. And we know that that is the same as A. So it looks like whenever it's an odd exponent, A to the odd exponent is just A. And whenever it's an even exponent, we have the pink and the green guy. Okay, so I'm going to say, therefore I can conclude that A to the 2n, okay, which was the even guys, so 2n, what color do I want to use? 2n is going to be equal to, whenever it's even, it's this matrix 1, 0, 0, 1. And A to the, whenever it's odd, so 2n plus 1, we have that it's just A. And that's for all values of all positive integers n. Okay, so I think I'm going to leave it there because I'm just too exhausted. See you in the next section.